This is the famous Grignard reaction in which the nucleophilic carbon attacks a carbonyl group. The result is forming of the valuable new carbon-carbon bond. But the important point is that there are two approaches for attack of the nucleophile, ending up with two different products in terms of stereoselectivity. This is the carbonyl group. As you see, it has a planar structure. Looking from this angle shows that the nucleophile can approach from above or below the plane of the carbon-oxygen double bond. Is it possible for the incoming nucleophile to attack only from one face? Which factors affect the approach of the nucleophile? These questions are related to asymmetric addition to the carbonyl group. In this video, I'm gonna explain the rules that govern the asymmetric addition to the carbonyl group from basic to advanced level. In recent years, programming has opened new doors in organic chemistry, helping chemists design reactions and catalysts, especially with Python. That's why I've been exploring Brilliant, who is sponsoring this video. Brilliant is an interactive learning platform that helps you to build skills in math, science, and computer science through step-by-step problem solving. I've been using the Python course, and what I really like is that you don't just watch lessons, you actively solve problems yourself. The courses are crafted by world-class educators from MIT, Harvard, and Stanford, and are designed for everyone from age 10 to 110. To learn for free on Brilliant for a full 30 days, go to brilliant.org/chemicator, scan the QR code on the screen, or click the link in the description. Brilliant is also giving our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Alright, now let's get back to chemistry. First of all, let's see what asymmetric addition is. A nucleophile can attack the carbonyl group from two faces. The probability of the nucleophile approaching from each side is 50%. So the hydroxy group in the final product could have different orientations. Each of them is called an enantiomer. One of them has R and the other has S configuration. Such a mixture of enantiomers is called a racemic product. Synthetic chemists are interested in finding a way to produce only one of the enantiomers. So when we get a product in which one of the enantiomers is dominant, we actually do an asymmetric synthesis. Instead of a racemic mixture, such products are enantiomerically pure, and our synthetic strategy is enantioselective. Asymmetric addition to a carbonyl group is also called facial selectivity, because there is a bias in the system that prevents the nucleophile from attacking from one face of the carbonyl. So one enantiomer in the final product becomes dominant. Now you might be curious how we can create a bias in the system and do an asymmetric addition to the carbonyl group. The answer is that we need a chiral environment. The chiral environment can come from the reagent. For example, using a chiral Lewis acid in the reaction can induce chirality. Another option is to use a chiral substrate. In this video, I focus on using a chiral substrate and explain how a chiral aldehyde or ketone control the stereoselectivity. Now take this reaction as an example. As you see, this carbon atom in alpha position of the carbonyl group is chiral because it's bearing 4 different substituents. When the nucleophile attacks the carbonyl group, 2 stereoisomers are produced, but one of them is a major product because of the chirality of the substrate. The important point is that this reaction is not enantioselective, but it's a diastereoselective reaction. Imagine this new chiral center has the R configuration, so the other stereoisomer has the S configuration. But the configuration of this carbon atom is not changed during the reaction. Imagine it has the R configuration, so the chiral centers of the final products are RR and RS. It means that they are diastereomers. So this is a diastereoselective reaction. I just wanted to clarify what the difference is between a diastereoselective and an enantioselective reaction. We found that the existence of a chiral center in the substrate induces chirality. Now let's take a look at these structures. All of them are chiral, but they are different in distance from the carbonyl group. If the presence of a chiral center always led to inducing chirality, all of these compounds should undergo a diastereoselective reaction with the nucleophile. But the reaction is diastereoselective only when the chiral center is near the carbonyl group, which is the center of the reaction. The reason is that the presence of a chiral center makes the two faces of the carbonyl group unequal. As you see in this compound, there is a chiral center in the alpha position of the carbonyl group. When a nucleophile approaches the carbonyl group from the left, it faces the blue sphere. But when it approaches from the right, it faces the green sphere. In other words, the nucleophile faces a different environment when it approaches the carbonyl group because of the chiral center. It means that the diastereotopic faces are always different in principle. But once the chiral center is far away from the center of the reaction, the two diastereotopic faces become equal because of the free rotation around single bonds. It means that the rate of the rotation around single bonds is much faster than the rate of the reaction with the nucleophile. So the incoming nucleophile fills the average environment. As a result, we can't expect any reasonable level of diastereoselectivity. Now the question is how a chiral center induces chirality in the product. To answer this question, we need a model. There are several models that describe the stereochemistry of adding a nucleophile to the carbonyl group, but we don't need to learn all of them. The Felkin model is a standard model that explains how chirality is induced at the carbonyl group. So if you read a paper or answer questions in your exam, this is the most accepted model. In this model, substituents are classified based on their size. So we have large, medium, and small substituents. For example, in this compound, phenyl is a large substituent, methyl has a medium size, and hydrogen is a small one. In the Felkin model, we use a Newman projection in which we look along the bond between the carbonyl carbon and the alpha carbon atom. Notice that none of the substituents should be eclipsed with the carbonyl group because it's very unstable due to steric hindrance. First of all, we should find the most reactive conformation. To do this, I'll show you all possible conformations by rotating 60 degrees around the central carbon-carbon bond. This model is used for both aldehydes and ketones, but here I'll go with an aldehyde. Let's get started with this conformer in which the large substituent on the right is perpendicular to the carbonyl group. Rotating the carbon-carbon bond by 60 degrees gives us this conformer in which the large substituent is positioned on the right side of the hydrogen. Another 60-degree rotation places the large substituents on the left side on the hydrogen. The next rotation places the large substituents perpendicular to the carbonyl group again, but this time it's positioned on the left. It's actually the opposite direction compared to the first conformer. After another rotation, the large substituent is placed near the carbonyl group on the left, and in the next conformation it's placed on the right side of the carbonyl group. With the next rotation, we get back to the conformer that we start with, so there is 6 possible conformations. Based on the Felkin model, the most reactive conformation is the one in which the large substituent is perpendicular to the carbonyl group. So these two conformers are the most reactive among the 6 possible conformations. The important point is that we don't want to find the most stable conformation. We should choose the conformation in which the large substituent is perpendicular to the carbonyl group. Even if this conformation is the minor one in the mixture, the reaction proceeds through this pathway. Now we should make a decision about which of these conformers is more reactive. To find the answer, we should see how the nucleophile approaches the molecule. Here I show the nucleophile as a purple sphere approaching the carbonyl group. It might seem that it attacks perpendicular to the carbonyl group. That would mean the angle between the incoming nucleophile and the plane of the carbonyl group is 90 degrees. But in reality, the nucleophile approaches the carbonyl group at an angle of 107 degrees. The specific angle is called Bürgi-Dunitz trajectory. If you want to know why this happens, keep watching until the end. Now let's go back to Newman projection. Notice that there are 3 possible angles from which a nucleophile can attack the carbonyl group. The first one is between the large and medium substituents, the second is between the large and small substituents, and the third is between the small and medium substituents. To minimize steric repulsion, the nucleophile attacks from the direction opposite to the large substituents, and this attack occurs along the Bürgi-Dunitz angle. In the conformation on the right, when the incoming nucleophile approaches the carbonyl group, it faces the medium-sized substituent, but in our conformation, it faces the small one. Obviously, steric hindrance in this conformation is less than the other conformation, so the transition state is lower in energy. Because of that, this conformation is more reactive. After finding the correct orientation of the approaching nucleophile, we should draw the final product. To do this, we place the nucleophile on the left, opposite to the large substituents on the back carbon atom. The hydroxyl group is positioned the upper right, and the hydrogen is placed in the lower right. Now let's put all of we learned into practice. In this question, we want to predict the stereochemistry of the product. This is a Grignard reaction in which the ethyl group is added to the carbonyl group to produce the chiral alcohol. First of all, we replace the substituents in the Felkin model based on their size. Phenyl is the bulkiest one, so it's a large substituent, and it should be perpendicular to the carbonyl group. Methyl is a medium-sized, and hydrogen is a small substituent. Notice that no matter what the stereochemistry of this carbon atom is, we go with this conformation based on the Felkin model. Next, the Grignard reagent attacks from the small side of the compound, so here is the final product with the correct stereochemistry. But this is not the end. We should draw the product in a standard form. It means that the longest chain of the product should be drawn in the plane of the paper. This could be a little bit tricky. This is a 3D visualization of the Newman projection. First of all, we should find the longest chain on each carbon atom. On this carbon atom, ethyl is the longest one, and the phenyl group in the longest chain on the other carbon atom. In the next step, we redraw the Newman projection. Look at the compound in the question. Usually, we draw the product in such a way that the longest chains on each carbon atom are n-tied to each other. Here the phenyl group is pointing upward, just like in the structure of the carbonyl compound, and the ethyl group is pointing downward. We do the same thing with the Newman projection. By rotating the front carbon atom anti-clockwise, the ethyl group is placed downward. The phenyl group is also pointing upward by rotating the back carbon atom. Now we should change our viewpoint. Instead of viewing the molecule from the front, see it from the side. Now it's very simple. Just draw what you see. This is the ethyl group pointing downward, and this is the phenyl group pointing upward, and they are n-tied to each other. The hydroxy group is pointing toward you, so draw it out of the plane. The methyl group is also pointing toward you, so draw it out of the plane. This is the correct stereochemistry of the final product. As you see, the methyl group and the hydroxy group are on the same phase, so we can say that the syn diastereomer is a major product. By using this approach, we can answer any question, but notice that you should do all of these steps in your head. Let's get into another example. This time, a ketone reacts with lithium aluminum hydride. As you see, the substituents are like the previous example. Based on the Felkin model, we draw a Newman projection in which the large substituent, in this case the phenyl group, is perpendicular to the carbonyl group. And notice that here there is an ethyl group instead of the hydrogen in an aldehyde. Next, the hydride attacks the carbonyl group from the least hindered side, resulting in this conformation. Make sure that the nucleophile and the large substituent on the back carbon atom are n-tied. Now we should redraw this Newman projection in a standard form. Before I go to 3D space, train your brain to do it by yourself. Pause the video and have a try. Look at the ketone. The phenyl group, which is the longest chain on this carbon atom, is pointing upward, so we don't change it in the product. Ethyl is the longest chain on the other carbon atom. In a standard form, the two longest chains should be n-tied to each other, so we draw the ethyl group pointing downward. Now we do the same thing with the Newman projection. Rotate the front carbon atom to put the ethyl group downward and keep the phenyl group upward. Now change your viewpoint. Looking at the molecule from the side shows that the methyl group is out of the plane, but the hydroxy group is far away from you, so draw it in the opposite direction. So in this case, the methyl and the hydroxy groups are n-tied to each other. Therefore, the n-tied diastereomer is a major product, unlike the previous example. When using the Felkin model, you should check whether an electronegative atom is attached to the alpha carbon atom or not, because it changes the conformation. Remember to put the electronegative atom perpendicular to the carbonyl group, even if it's not the bulkiest substituent. Let's explain it with an example. In this question, sodium borohydride attacks the carbonyl group but has an electronegative chlorine atom in its alpha position. Draw the Newman projection based on the Felkin model. If you put the ethyl group perpendicular to the carbonyl group because of its larger size, this leads to the wrong stereochemistry. This is the electronegative atom effect. Put the chloro atom perpendicular to the carbonyl group, no matter whether it's larger than the ethyl group or not. Next, the hydride attacks from the less hindered side. Now redraw it in a standard form. Obviously, this substituent with 4 carbon atoms is the longest chain, and it's pointing upward. Ethyl on the other carbon atom is the longest chain there. We put it downward because the two longest chains should be n-tied to each other. To keep it simple, I show the 4 carbon substituent with R. Now rotate the carbon atoms, put the R group upward and the ethyl group downward. Change your perspective when you see the Newman projection from the side. Both the hydroxy group and the chloro atom are pointing toward you, so draw them out of the plane. As a result, the seen diastereomer is a major product. You might be curious what the electronegative atom effect is and why the electronegative atom changes the conformation. We should find the answer in orbital interaction. The pi bond in carbon-oxygen double bond is created by side-to-side interaction of p orbitals on the carbon and oxygen atoms. This interaction results in creation of 2 molecular orbitals. The pi electrons occupy the first molecular orbital, so it's a bonding molecular orbital and it's called the HOMO orbital. The second molecular orbital is empty and has a higher energy. It's an anti-bonding orbital and is called the LUMO orbital. Unlike the bonding orbital, the lobes of these orbitals are not in the same phase. Because of that, this molecular orbital is anti-bonding in nature. Another point is that the p orbital on the oxygen atom is smaller than that on the carbon atom. Because of its high electronegativity, it withdraws electron density toward itself, resulting in a smaller p orbital size. Now let's go through the molecular orbitals of the sigma bond between carbon and an electronegative atom. I take CCl bond as an example. Just like the pi bond, the sigma bond between carbon and chlorine has 2 molecular orbitals with different energy levels, and the electrons occupy the first molecular orbital. Unlike the double bond, orbitals in a sigma bond have head-to-head interaction. So in the bonding orbital, electron density is located between the 2 atoms. The anti-bonding orbital has higher energy. Look at the shape of the orbitals. The important point is that in the empty anti-bonding orbital, there is no interaction between the 2 atoms, and the orbitals are extended outside the bond. Here we see the conformation in which the CCl bond is perpendicular to the carbonyl group. This is the LUMO orbital of the carbon-oxygen double bond, and this is the anti-bonding orbital of the CCl bond, in which the orbitals are extended outside the bond. What happens here is that the LUMO orbital of the carbonyl group and the anti-bonding orbital of the CCl bond are in the same phase, so they have a constructive interaction. In other words, they combine with each other to create a new molecular orbital. We can show this combination as pi star plus sigma star orbitals. This overlap between orbitals is only possible when the CCl bond is perpendicular to the carbonyl group. This kind of orbital interaction is called stereoelectronic effect. If you want to know more about this concept, check out this video to understand orbital interactions at a deeper level. Here I show the orbital overlap resulting from pi star plus sigma star orbitals. On the left, we have the pi star orbital coming from the carbonyl group, and on the right, we have the sigma star orbital coming from the CCl bond. When they combine together, two new molecular orbitals are created. Now let's see the nucleophilic addition to the carbonyl group through the lens of orbital interaction. In nucleophilic addition, the HOMO orbital of the nucleophile, which is full of electrons, interacts with the empty LUMO orbital of the carbonyl group. In other words, the nucleophile is a donor group and the carbonyl group is an acceptor. Electrons move from the nucleophile into the carbonyl group. Actually, it's a HOMO-LUMO interaction. Here's an important role. In a HOMO-LUMO interaction, the lower the energy of the LUMO, the more facilitated the orbital interaction is. In other words, the LUMO orbital is more accessible when its energy is lower. Now get back to the molecular orbital diagram. Look at the energy level of the carbonyl group on the left. You can see that after overlap with sigma star orbital of the CCl bond, the energy of the new molecular orbital is reduced. The incoming nucleophile attacks this new molecular orbital because it's more accessible and the reaction occurs more easily than before the overlap. Now it's a good time to understand why the nucleophile attacks a carbonyl group at a 107 angle. Imagine that the nucleophile approaches the carbon-oxygen double bond at 90 degrees. As you can see, there are two interactions between the HOMO orbital of the nucleophile and the LUMO of the carbonyl group. The interaction with p orbital of the carbon atom is constructive because the orbitals are in the same phase. However, the interaction with p orbital on the oxygen atom is destructive because they are out of phase. When the nucleophile approaches the carbonyl group at 107 degrees, the destructive interaction is reduced, so the HOMO-LUMO interaction becomes more favorable. Alongside the HOMO-LUMO interaction, there is another interaction between the HOMO of the nucleophile and the HOMO of the carbonyl group. Here both orbitals are filled with electrons, so this is a repulsive interaction arising from 4 electrons. By deviating from 90 degrees to 107 degrees, the amount of this repulsive interaction is reduced. So these two reasons explain why the nucleophile attacks at 107 degrees instead of 90 degrees.